Okay, let's dive right into today's explainer. We're going to explore exactly how we transition from the total chaos of early shared hubs to the lightning-fast, switched point-to-point networks that you'll be troubleshooting out in the real world. So if you're studying networking fundamentals and stepping into the shoes of a network engineer, you are in the exact right place. We're going to look really closely at the physical layer of Ethernet. We're talking the actual wires, the light pulses, and the strict timing rules that make modern data flow possible.
Here is our agenda for this explainer. First, shared networks and collisions. Second, timing, spacing, and congestion. Third, the evolution of copper cabling. Fourth, gigabit speeds and encoding. Fifth, the power of fiber optics. And finally, number 6, troubleshooting physical layer faults.
All right, Section 1, Shared Networks and Collisions. Let's step back into the dark ages of networking for a minute.
Early coaxial bus topologies functioned a lot like a crowded, noisy room where everyone is just trying to shout over one another. Climbing this incredible ladder of speed from a humble 10 megabits per second all the way up to 10 gigabits and beyond, well, it required networking pioneers to constantly invent new ways to overcome the physical limits of sending and receiving electrical data. Signal timing remains absolutely critical as data throughput increases across these modern media. Why? Because at higher speeds, your tolerance for physical error basically vanishes.
So what happens when two devices transmit simultaneously on those legacy networks? Boom, a collision. When this happens, they immediately send a highly recognizable 32-bit repeating 1010 jam signal. This guarantees that every single device on the local area network detects the crash. It's a brilliant piece of the CSMA/CD protocol. That's Carrier Sense Multiple Access with collision detection for those keeping track. It acts like a massive stop sign for network traffic to prevent total chaos.
Moving right along to Section 2, Timing, Spacing, and Congestion.
The crucial point here is figuring out exactly how the network media recovers and maintains order after one of these messy collisions. Because, let's face it, identifying the crash is only half the battle. When you're managing traffic congestion, you're going to spot these failed, corrupted transmissions, and we call them runts. These runts are super easy to flag with your diagnostic tools because their short length, which is anything under 64 octets, automatically causes them to fail the frame check sequence test. Seeing a high count of runts is basically your first major clue as an engineer that you've got severe physical layer collisions or media issues.
Now, regardless of how much you upgrade your speed, Ethernet literally demands a breather. It needs a minimum stabilization gap called interframe spacing. This is a mandatory 96-bit time gap required between frames that lets the physical media stabilize and gives your devices time to actually process the incoming frame. And what's really fascinating here is that while that 96-bit rule stays exactly the same, the physical time it takes shrinks proportionally as your network speeds exponentially increase.
So how do we prevent repeated network transmission collisions? Well, the CSMA/CD process steps in and assigns a random backoff timer to each device. This ensures they don't just jump right back onto the wire at the exact same millisecond. After that jam signal clears the wire, each station essentially rolls the dice. If they happen to collide again, that random backoff window actually gets larger, giving the network a much better chance to breathe and clear out the congestion.
Let's move to Section 3, Evolution of Copper Cabling.
Let's see how all this theory translates into the actual physical copper wires you'll be running and diagnosing. As future engineers, you absolutely must memorize these limitations. Notice our transition from the old 500-meter coaxial thicknet shared buses over to the modern 100-meter dedicated twisted pair topologies that we use in switches today. We basically traded sheer cable distance for dedicated collision-free point-to-point links. Modern twisted pair cables hooked up to intelligent switches meant we could finally ditch the shared bus, and that made those old hubs completely obsolete.
Which brings us to Section 4, Gigabit Speeds and Encoding.
Moving past fast Ethernet, simply pushing more voltage through a wire wasn't enough anymore. We had to get much smarter with our encoding to avoid total physical link failures. At gigabit speeds, bits are firing so fast they become incredibly susceptible to noise and timing errors. While fast Ethernet used 4B/5B encoding, gigabit fiber relies on 8B/10B. These encoding schemes are totally essential for maintaining synchronization in high-speed links because they insert extra bits to ensure continuous clock timing. You're maintaining that vital timing at the cost of overhead, meaning you actually require a 1250 megabit binary transmission rate just to achieve a clean gigabit of actual data throughput.
And just take a look at the sheer, incredible complexity of 1000 base T over copper. It's using all 4 wire pairs simultaneously with advanced hybrid echo cancellation. Because data is flowing in both directions on all pairs at the exact same time, it creates really complex voltage patterns. In fact, to squeeze a gigabit out of legacy wiring, the interface uses up to 17 distinct voltage levels. Honestly, it looks more like an analog wave than a digital signal. It's an absolute marvel of modern engineering.
Okay, Section 5, the power of fiber optics. Copper is great, but it has its limits. So it's time to look at the ultimate physical layer upgrade, a medium that completely revolutionizes our transmission boundaries. By trading electrical copper signals for fiber optic light pulses, we completely eliminate electromagnetic interference, and we drastically increase our unrepeated bandwidth and distance. With fiber, you aren't fighting electrical noise or ground loops anymore. You are sending pristine light down a strand of glass, unlocking massive point-to-point bandwidth over miles, not just meters.
Now, you absolutely must know the technical differences between short wavelength SX and long wavelength LX multimode fiber configurations. This is crucial to accurately specify hardware for your point-to-point switch lengths. SX uses an 850 nanometer wavelength, while LX uses a 1300 nanometer wavelength. Matching the right transceiver to the right fiber core size is a foundational, absolutely critical skill for any network engineer if you want to prevent link failures.
Finally, Section 6, troubleshooting physical layer faults.
Let's bring all this theory together into the professional troubleshooting steps you'll actually use for managing network traffic congestion. When a dead network drop lands on your desk, your very first steps are verifying the cable category, ensuring timing constraints aren't violated by excessive cable lengths, and checking for drop frames. And why do frames drop? Well, if media congestion causes a collision attempt to fail 16 times in a row, the MAC layer just throws its hands up and throws an error to the network layer. Also remember, if your copper runs are over 100 meters, physical link failure is going to occur simply because those strict timing constraints we discussed earlier are being violated. So, with all this foundational knowledge in mind, and leaving the days of legacy hubs and noisy collision domains firmly in the rearview mirror, I leave you with this. As we push into 40, 100, and even 400 gigabit speeds, what physical limits of light and copper will your generation have to conquer next? Keep exploring, keep questioning, and I'll catch you in the next explainer.